All right, so this position that we're calling the center of our coordinate system, the North Star, is actually quite a variable thing because of the fact that, remember, you have to look up from the Earth's axis to see the direction of true north. Okay, so true north then is this direction, but the direction of true north then is going to deviate from the position of the North Star. This is just our current pole star. But Vega, another star that is fairly high in the sky right now, will be our pole star in another 14,000 years. And Thuban was our pole star 3,000 years ago. And so we can see how this traces out the path that true north takes over our 26,000 year time span. There's Thuban at 3000 BC. Here's Polaris. Notice that Polaris at our present moment is not exactly true north, but rather is about a half a degree off from true north. But as time goes on, in about 8,000 years, one of the stars in Cepheus will be close to the North Star. And then Vega will be close to being our North Star in about 14,000 years. But you can see that in the entire cycle of 26,000 years, there's only, this is about the only time when a somewhat major star that's fairly bright is really, really close to that line. Okay, and so if I ask you a question like 2,000 years ago, there was no North Star, that would be at AD1, the answer to that would be true. Even though Polaris still exists, it wouldn't be the North Star anymore 2,000 years ago. And 2,000 years from now, I mean, this star might be close to being a pole star, but it's not a very bright star. And it's not exactly on that line. Okay? And so if we want to try to make sense out of all of this, we can do that with a star wheel. Now these, I have given you a link so that you can download something that you can put together that's a star wheel. That should work pretty well. Or you can buy these from the bookstore. This is one of the things that's on the list for our necessary equipment that we need for the semester. And so you'll notice here in the center of this, there's a hole punched in it, and that hole is the North Star. Okay, and so you'll notice then as I turn the star wheel that all of the other stars appear to go in a counterclockwise circles around the North Star. Okay, and so if we wanted to, let's say, use this to find the part of the sky that we could see, say, this evening, the way that we would do this, and here I'll put this on the data projector here, is first we would find our date. Okay, so our date is September 3rd, when I'm doing this video at least. And so what you'd want to do then is take the date, here it is, September 3rd, and put it on the time when you want to view. So let's say that I want to, and by the way, I checked the viewing conditions, and it's supposed to be fair this evening, okay, and probably for the next few nights. But here on September 3rd, I would point September 3rd at 9 o'clock. Okay, and so that's the first step then in getting your star wheel to work. Just take date line up with viewing time. So that will then give you that part of the sky that you can see. And so that's what I've done here then. And so now we have that part of the sky that can be viewed from our vantage point here in San Luis Obispo, approximately, at 9 o'clock this evening. Okay, so now what I'd want to do is take the star wheel and hold it over my head like this, okay, and point the north pointer of the star wheel at true north. Okay, so you don't want to hold it down here, because then you're going to see the mirror image of what you're interested in. You have to have it up there. Okay, and so hold over your head. And point north corner in the northerly direction. So if I do that, and I hold this thing up there like that, then what I see for the Big Dipper and its configuration is going to look, let's put this back down here, so that if you're pointing toward the north, this is what you would see too. It's going to look something like this. Not exact. Just roughly, something like this. And so then these two stars are what we call the pointer stars. Sorry, this needs to go this. There, now we've got it. So now these are the pointer stars. And so they'll point up here to the North Star. So the Big Dipper is fairly easy to find, so that if you look in the direction of north, you should see the Big Dipper in the lower part of the sky. And so then if you measure an angle as you're looking toward the north of 35 degrees, that should get you into the right perspective where you'll be able to see these pointer stars from the Big Dipper pointing at the North Star. And so that's another way then to find the North Star, is to just follow the pointer stars from the Big Dipper. And so we know then that the Big Dipper is down here. If we're looking toward the north, that's something like, it's a little more of an angle than this. If this were a clock, this might be like, say, 7 o'clock or something like that. So this would be 6, 7, 8. So if you're thinking in terms of something like that, then it would be pointing off in that kind of a direction. Now, what's going to happen with all of the constellation patterns is that as the nighttime and the daytime goes by, they're going to rotate. So look at what's happening here with the Big Dipper. See if I can zoom in on this a little bit. Okay, so here's our Big Dipper. And So we want to keep going. So this is 10, 11, maybe 12, 1, 2, 3, whatever. Okay, so let's say that you're walking along and you've got one of those cool little night lights on, and but you just make one little tiny mistake and you accidentally fall off the side of a cliff. You land in some water and then you go over a waterfall and you're knocked unconscious. So you wake up, you're scared, you're cold, and what are you going to do? Well, remember this lecture, because we know that at 9 o'clock p.m. this evening, the Big Dipper was down here. And so now we see it over here. This looks like kind of like maybe 90 degrees, okay, away. So it's still the same pattern of stars, but it's been rotated as it goes around the North Star. And so then the pointer stars, then you'll note, are still pointing at the North Star. And so can you see then that if this is 90 degrees, let's say, that means that we've gone through a quarter of a day, right? Because in 24 hours, the Big Dipper will be back around to this point at 9 o'clock in the evening again. It'll be September the 4th instead of September the 3rd, but that's not going to change things much, only by about 1 degree. So it's still going to be pretty much the same position 24 hours later. So by knowing what the Big Dipper was, how it was oriented at some standard time, and then measuring the angle, you can see here that this must be, well, 90 over 360 equals 1/4 of a day later. Right? Because if it were 180 degrees, it'd actually be daytime, probably by then, 9 o'clock in the morning. But, so this would be 9, 10, 11, 12, 1, 2, 3, 6 hours later. So this must be 3 o'clock a.m. So what you just did, by identifying the position of the Big Dipper at some other time and measuring it with respect to the position of the Big Dipper at some standard time, is you've used the Big Dipper as a clock. Okay? And so that you can do that. But all you have to know is what the calibrated time is for the Big Dipper at a certain time of the year. So that will change. And so it won't always be here. In another month, it might have moved a little bit. It might be more directly below the North Star. But still, the amount that it changes could be used for you to basically determine what's going on with the Big Dipper as a clock. Now, another thing that you can do here is you can look on the other side of the North Star. And if you look over there, you'll see Cassiopeia. Okay, so Cassiopeia is here, and that's kind of exactly on the other side of the North Star from the Big Dipper. And so what you would tend to see then over here would be a, as we're viewing from the Earth's point of view, we see the Big Dipper, North Star, Cassiopeia would be up there. But here, this big W would look like it's here with respect to where you are at 9 o'clock in the evening. And so you look up, you'd see the Big Dipper, you'd see the North Star. If you look at equal distance on the other side of the North Star, you'd see Cassiopeia. So that kind of frames it a little bit for it, so that you have another constellation that's fairly easy to see that can help you to use the Big Dipper as a clock. Okay? And you can also get north by finding the Big Dipper and then going up to the North Star. You also have used it as a compass. Okay, so you've used it as a compass and you've used it as a clock. Okay, so this is what the ancient maritime navigators did. They were able to determine where they were by having a good compass, and then they had a good method of measuring angles, and were able to find then what their north latitude was. So the basic tendency then of the sky is that each evening the stars appear to describe counterclockwise circles around the North Star. And so this is just an apparent effect, though. And so you might wonder, well, first of all, why is it that the North Star always stays in the same place? Because that's really what allows all of this to happen. From our point of view, the North Star stays in the same place. And it's the only star that does. So I'm saying here, notice I'm saying seems to, because it's just from our point of view. So let's see how this would work. Here we've got the Earth. Here we are in San Luis Obispo, here at 35 degrees north latitude. So we're standing here. We look toward the north, and then we look an angle above the north horizon that's equal to our north latitude by 35 degrees, and there it is. That's the North Star. You may be saying, well, how does this line and that line end up in the same place? And the answer is, the North Star is actually way farther away, so that these two lines are essentially parallel. The North Star would be like on the moon or something from our point of view here. And so these two lines over much longer distances like this are essentially parallel to each other. If we went all the way out to here, you wouldn't be able to tell the difference between the two lines, even though they're not quite parallel. They're so close to being parallel, they might as well be. And so this is, by putting the North Star on our picture, we're not putting it nearly as far out as it needs to be. Okay, so here's the North Pole then. Here's how we see it. But then let's imagine that this is a part of the year when the night goes for at least 12 hours. So then you're over on this side, 12 hours later. So how could the North Pole still be looking like it's in the same place? Well, because here you're looking toward the north still, and then to see the North Star, you're looking at an angle above the horizon that's equal to your north latitude. So everything with respect to your coordinate system, you're still looking north, you're still looking at the same angle above the horizon. So that means you're looking in the same place. And so that's why the North Star doesn't seem to move. Is that, but while that's happening, a star here that looked like it was on the right, over here it would look like, from this point of view, you're looking at the North Star, it would look like the opposite, look like it's on the left. So it would seem as though it had gone from here around to there. So you're completely changing, kind of turning your perspective around in order to see it from that different point of view. And so that might take a little bit of thinking, just to get used to the idea of trying to look at the Earth not from the Earth's perspective, but rather from a point of view in which the Earth is turning and is looking at other things from differing points of view. And so that is what tends to scramble people's minds just a little bit when getting used to the concepts that are associated with astronomy. Okay, so, but this is one of the main effects that you can expect to see if you're looking in the vicinity of the North Star. And so here, in this next picture, we see a time-lapse photo of the North Star with the other stars, they're looking kind of smeared out. But we can see in this overexposure that they are in fact describing circles around the North Star. Okay, and so that proves it. The only thing that you might wonder about here is, well, okay, that's great, but what about when it gets to be daytime? You know, then you wouldn't be able to see the stars anymore. So why do we see complete circles if it's nighttime only half of the whole day? Think about that for a second. Why are we seeing complete circles if it should be daytime half the time? Shouldn't that cut off half of our circle so that we'd only see a semicircle and then be bright? Well, that's true except when it's winter at a high latitude in the northern hemisphere. Okay, so let's say it's around December or so. Then at that point, here's the sun. So this would be summer. The Earth's axis is leaning toward the sun. This would be winter. Here's the Earth's axis leaning away from the sun. So this side, this is the equator here. This is the Earth's axis. But here's the side of the Earth that's being illuminated by the radiation from the sun. So notice then that up here near the North Pole, we're not getting any light, day or night. And so that's when that photo was taken. It was taken when you were up here during winter in the northern hemisphere, when basically the nights might last, well, they could last a really long time. They could last 24 hours if you get close enough to the sun. If you're up in, say, Anchorage, Alaska, even at that point, you're kind of here, but you still have maybe 20 hours of night and only 4 hours of day. But then you get up all the way beyond where that shadow even ever reaches, so that you're always in perpetual darkness for at least a month or two out of the year or more. Then you could take a picture like that when the stars would describe complete counterclockwise circles, and you'd be able to see it during the entire time.